Good morning, class. Now in this lecture, lecture 19, we'll solve a few other circuits. So in last class, I derived for RC circuit response. So in time domain or a Laplace domain, the expression for Vc of t, that is we got Vc of t equal to what? V infinite plus V of 0 minus V of infinite e power minus t by 2. So the change in voltage across capacitor we derived. So in Laplace domain also. So in time domain also we can derive. In Laplace domain also we derived. Now in this section we deal about RL circuit. This inductor having with in here initial current I0. Now we need expression IL of t or I of t. So the loop equation I of t. So this is input voltage V. So at t less than 0, before switch is operating, what is the initial voltage, initial current here? So IL of 0 equal to what here? I0. So initially this inductor was charged from other circuit and is having I0 current. Now we replace this I0 current in this circuit, and we at t equal to 0 we are switching on this circuit. So at the before the switching on the circuit, the current I0 at I0 equal to what? IL initial voltage, initial current is I0. Now at t greater than 0, this is the main step we need to understand. At t greater than 0, we have to represent the above circuit in Laplace form. Okay. So the main item is here Laplace of a constant is what? Some k is what? Laplace of k equal to k by s. Laplace of this L is inductor is SL. So the Laplace transform of an inductor having initial current I0, this is t domain, and now we should represent this inductor in time in Laplace domain is, we initially drawn this L into I0 and this is Ls. This is S domain representation. Since we are converting this time domain, this is time domain. At t greater than 0, we should represent this circuit in Laplace domain. So representing this Laplace domain, each element we have to represent this. So the voltage source, this Laplace of a constant is k by s. So Laplace of voltage is a constant voltage. So this is we can represent by V by s. The switch is on here at t greater than 0. The R is represented same only. So at t time domain, R and the Laplace domain both are equal. Now coming to this inductor is represented like this. So you have to remember this Li0 Ls. So how we replaced this representation of inductor in Laplace in domain we dealt before. So directly I am giving this. Now we need the response. IL of S. Okay. So we need the response IL. For getting this response IL of S, just we have to do is just a loop equation. So applying loop here, loop analysis, or apply KVL. What we have? Minus V by S plus R into IL of S plus Ls into IL of S minus L I naught equal to 0. So we get the IL term R plus Ls. So we take the constants outside, that side, L I naught plus V by S. So we need a response IL of S. Okay. So if is equal to, so you rearrange this above that circuit, Ls plus R. So in denominator we have to represent it S plus A form. So we take L outside here. IL of S equal to S L I naught plus V. So if you take this L outside, this entire thing L by S into L plus S plus R by L. So this can be represented as a S I naught LL cancel plus V by L by S into S plus R by L. So we need L of S we got. So for getting inverse Laplace of this component, we need to do partial fractions here. So partial fraction of above this partial fraction here. So L of S can be represented as A by S plus B by S plus R by L. Okay, take the LCM here. A into S plus R by L plus BS by S into S plus R by L. This is IL of S. Compare the equation this and this. So L of S equal to L of S. So comparing both equations, this is one, like comparing both equations, you get the equation comparing the numerator S plus R by L plus BS equal to S into I naught plus V by L. So compare the coefficient of S. So coefficient of S here, this term is here having A. Coefficient of S you are having B. The coefficient of S is I naught. The coefficient of constant, compare coefficient of constant here. In this section the coefficient of constant is A into R by L. No coefficient of constant here. Here we have V by L. So L will cancel. Now A equal to what? V by R. Okay. Substitute this A in this above equation. Then B equal to, you will get I naught minus V by R. So you got A and B for this equation. So for finally you will be obtaining IL of S equal to, substitute A and B in this equation. So this, let us take this equation as 3. Substitute A and B in 3. You will be getting A equal to what? V by R by S minus plus I naught into minus V by R by S plus R by L. So Laplace inverse. So Laplace inverse we take, this is the constant by S. So Laplace inverse of K by S equal to what? K. Again Laplace inverse of a constant K by S plus A equal to what? K into e power minus at. So here we Laplace transform of above equation, we get V by R plus I naught minus V by R into e power minus t by tau. T by e power minus t by power minus R by L into t. So here R by L can be represented as t by tau. So tau will be equal to what? L by R here. So this is the final expression you get through Laplace domain. So in time domain also, what we will get here, in I naught I of infinite plus I naught minus I of infinite e power minus R by L into t. So I of infinite is equal to what? At steady state in time domain, I of infinity means we will short this circuit inductor. So I of infinite equal to what here? V by R. So this is the V by R. Okay, so in whatever the method in time domain, we used to calculate this all these things by differential approach and integration process. Simply in Laplace domain, we just converting this inductor of having initial current to Laplace domain. So is the main thing you need to remember, and you need to analyze this thing. If we you are able to transform this inductor, we have initial current I naught in any circuits, not only in the RL series circuit, the combination of series and parallel circuits, if consisting of RL elements in any circuit, you can solve easily through Laplace transform. So you can obtain the final expression of current I of t, IL of t easily. The next, now let us solve the main section of Laplace transforms here. So in time domain, I gave as assignment, second assignment, a few circuits to solve. So in time domain, you people solve that. So finding initial value, finding final value, and time constant and all. Now, actually, I gave this about six or seven sums, and in that sum, one RC circuit will solve now in Laplace domain. Okay, so RC circuits, solving RC circuits in S domain. So S domain or Laplace domain, both are equal. So S means is a frequency here, complex frequency. So here the circuit you need to solve is this is 50 volts. This is 1 microfarad. This is 500. This is also a voltage source having a voltage 100 volts. Okay. Now I need expression of this is position 1. So the switch is acting initially at 1 for long time. In position 1 for long time, at t equal to 0, switch it to terminal. So now after switching, they are asking you to find Vc of t, the voltage expression. Okay, voltage across capacitor expression. So in Laplace, we'll solve this here. So initially at t less than 0 condition, so after switching only you to switch to Laplace. Before switching, we need to in time domain. At t less than 0, we need to find initial voltage across capacitor here. So the circuit at t less than 0 is what? So at initially, before switching, the capacitor is already charged for a long interval of time. So we replace this circuit at t less than 0 as like this. So Vc of 0 we represent. So now Vc of 0 equal to what? There will be no voltage drop here. So voltage voltage across this terminal is 100 volts only. Okay, this is the initial condition of this capacitor before switch on. Okay, now at t greater than 0, the condition is the above circuit has to transform in Laplace domain. Okay, represent the above circuit in S domain. This is the main step in converting time domain to Laplace domain. So from position 1 to 2, the circuit after time switch is operated is this is the initial voltage. This is a capacitor 1 microfarad. So this is the initial voltage Vc of 0. So we need to confirm Vc of 0 is equal to 100. So you need to transform this circuit to Laplace domain. So Laplace of constant is, so let us take this 50k. So Laplace of this constant source is 50 by s. So Laplace this capacitor is 1 by cs, that equal to 10 power, capacitor value is 1 microfarad, 10 power 6 by s. So initial this voltage is 100, Laplace of constant is 1 by s. So the right side of corner you need to represent this capacitor time domain. When converting this capacitor having initial voltage V0, when converted to S domain, it should be represented like this. So this is in time domain, we are representing this time domain capacitor into this form. So represented this capacitor in S domain is the main issue here. If you did exactly how the representation, half of the sum is completed here only. So we need what? Vc of t. So here in loop, so by loop analysis we find Ic of s. Now after getting this expression by loop analysis, so apply loop here, apply KVL equation. So this is the voltage cell. So minus 50 by s plus 50k into Ic of s plus 10 power 6 by s, this is s, into Ic of s plus 100 by s equal to 0. So we need Ic of s here. So Ic of s equal to 50k into plus 10 power 6 by 6 by s. So take this constant values there that side. So minus 50 by s plus 50 by s minus 100 by s. So you will getting Ic of s equal to what? 50k s plus 10 power 6 by s into minus 50 by s. So take Ic of s equal to minus 50 by 50k s plus 10 power 6. We need a s plus a form. So minus 50 by 50k, take this 50k common, so s plus 10 power 6 by 50k. So this is the expression, you get 20. So this is Ic of s. So Ic of t equal to what? Inverse Laplace of Ic of s. So this is the constant. So the value of this is 10 power minus 3. 50 divided by 50 into 1000. So you are having, this is the minus of 10 power minus 3 by s plus 20. So inverse Laplace of Ic of s is equal to, this is in the form of, so you are using inverse Laplace of this formula, k by s plus a. You need to represent that. So k into e power minus at. So this inverse Laplace of this thing is 10 power minus 3 e power minus 20 t. Okay. This is Ic of t. So we need actually what? Vc of s we need. So in general Vc of s equal to, you can write So getting we got IC of S here. So IC of S is this. So VC of S equal to 1 by 10 power 6 S into IC of S plus 100 by S. This is the voltage we need. So voltage drop across this capacitor and plus voltage of this voltage source. So this is the VC of S. Now 10 power 6 by S into IC of S is this. So IC of this is also IC of S. We represent this here. 10 power minus 3 by S plus 20 plus 100 by S. So solving this above circuit, above equation 10 power 6 into 10 power minus 50, sorry, 10 power 6 into minus of 10 power minus 3. So this will become minus of 10 power minus 3 10 power 3 sorry 10 power 3 by S into S plus 20 plus 100 by S. So take the LCM here. So minus 10 power 3 plus 100 into S of 20. So you will be getting minus 10 power 3 plus 100s plus 100 into 20. So 2000 by S into S plus 20. So we need to solve this thing. So VC of S equal to, you got minus 10 power 3 plus 100s plus 2000 by S into S plus 20. So 100s plus 1000 by S into S plus 20. So take the partial fraction of this. A partial fraction by partial fraction, the above equation can be turned into VC of S equal to A by S plus B by S plus 20. Now take the LCM here. A of S plus 20 plus BS by S into S plus 20. So this is equation, let us take this equation 1, this is equation 2. Comparing equation 1 and 2, so we got the equation, comparing the numerator A of S plus 20 plus BS equal to 100S plus 1000. So comparing the quotient of S. So A plus B equal to what? 100. The quotient of constants. So constant is here. The constant is 20A equal to 1000. So by this solving those equations, this A you will be getting 500. So B you will be getting minus 400. So VC of S equal to, substitute A and B here. So this equation will be turned into inverse Laplace. By applying inverse Laplace, you will getting VC of t. VC of t equal to inverse Laplace of VC of S. So inverse Laplace of constant by S is constant. So inverse Laplace of k by S equal to k. Inverse Laplace of k by S plus A equal to k into e power minus at. So you are using these two formulas here. So you need to write these equations here. So inverse Laplace of this equation is 400 into e power minus 20t. So you just cross check what you have done in time constant in previous assignment with this equation. So we just got this expression in time domain doing Laplace only by converting this capacitor initial having voltage V0 to S domain. So this is the main thing you need to remember. After this, the normal mesh and loop equations only. So you can get the VC of S directly by node analysis. So we'll take this as a node here. So for this node equation is VC of S minus 50 by S by 50k plus VC of S by minus 100 S by 10 power 6 by S. You can solve VC of S directly there. So in some cases they may ask you to find IC of T also. So in that form you can do this up to here. So getting this expression is enough there. So in case they ask me VC of T means you need to do this next procedure step. So in next class we solve one circuit on inductor and we'll do two RLC component combination circuits. So in 2 or 3 lectures we'll finish this transients. Thank you.